And who knows, I might actually prove something. I wouldn't bet on it, though. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I pray for the students that just be able to use the rest of this semester, Lord, for your glory, Lord, and guide our steps, Lord. In your name I pray. Amen. So we'll not have a meeting Wednesday because at least 2 of you have real analysis tests. So on Thursday, you know which 2 of you are.
I mean, measure your theory. It's a little bit related to real analysis.
It is related, but
Cantor said, so it will help.
well, maybe. So what I'm hopefully going to discuss for the remainder of this course is measure theory. And we are following Princeton, I can't spell, Princeton, there's an N in Princeton, well, you know. This is Princeton Lectures and Analysis, Part 3. Real analysis. By Stein, let's see, Elias M. Stein and Remy Shakarachi. So I will try not to mispronounce their names further and just say that these professors, it's a really fantastic series of analysis books. I've asked the question on the Math Stack Exchange, like, what should I be looking at for analysis? What's a good, how can I complete my understanding of analysis at the undergraduate level? And what I found the dominant answer seemed to be is to study this 4-part series from Princeton's Lectures and Analysis sequence by these two gentlemen. The first part in the 4-part series is on Fourier analysis, and it just sort of sets the table and asks the questions that need to be asked. The second in their series is on complex analysis, and that book is really, I mean, if you find yourself taking a complex analysis course in grad school, you need to have that book on your table and be looking at it. And you probably will, because it's probably going to be your text at a lot of schools. And then there's this one, which we were going to cover the first couple chapters in, and then part 4 is on functional analysis, right? Which I won't have anything really much to say about. But if you study these 4 books, then I would say you sort of have like a Dummett and Foote level treatment of analysis, which is maybe more than you should have, but a comfortable basis to go to grad school. Anyway, so his introductory chapter, he starts with I won't have much to write about the introduction chapter. I just want to talk about what's in it, okay? So his introduction chapter, he starts with this quote from Hermite. I turn away in fright and horror from this lamentable plague of functions that do not have derivatives. All right, so this 19th century analysis was sort of us discovering how calculus, as set forth by the masters like Newton, Leibniz, others, there were some problems, right? And a lot of those problems rested on what kind of functions we were working with. Really, there's really two things. And so, like, first point he makes is about Fourier series. He points out that when we take a Fourier series, we calculate Fourier coefficients, all right? And so if calculate these Fourier coefficients, and they will give you something in what's called L2Z, which is sequences, L2Z with, the 2 is referring to the norm, the 2 norm. And here's what he says. He says, each Riemann integrable function gives you a sequence by, you can calculate the Fourier series. But then if you reverse the question and say, okay, well, suppose I've got a sequence of coefficients, does there correspond an integrable function? Can I invert that idea? And he says, no. There are apparently sequences which are convergent in L2Z, and yet somehow there are not functions correspondent to those sequences. So there seems like there's something missing from that perspective. And he asked the question, what are the what are the quote-unquote functions, f, that arise when we complete the set of Riemann integrable functions? In other words, given arbitrary sequence in L2Z, what is the nature of the presumed function f corresponding to these coefficients? What are we missing by just looking at Riemann integrable functions? And then question 2 is, okay, so if they're not Riemann integrable, these functions we're missing, how do we integrate them? Right, so it's a question and a question. Then he talks about limits of continuous functions, and he points out, this is sort of the embarrassment. I'll write down this much. One of the great sort of annoyances of classical analysis is that the limit as n goes to infinity of fn of x, right, can equal to f of x. And so like f1, f2, f3, dot, 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 all continuous on the closed interval 0 to 1. That's a pretty nice interval. I mean, that's not a very complicated set for their domain. All of these being continuous, this limit existing, and not just for one x, but for each x, right? And yet, the limiting function not continuous, So this is a pesky thing. Like, continuity of functions does not transfer naturally over to the limit function. Do you guys know what example I'm talking about? It's a pretty easy one to come up with. Here's the example. I'm saying fn of x is just equal to x to the n. You can quite easily see that is what? I mean, is that continuous on 0 to 1? It's a power function, so yeah. And yet, what's the limit function? Right, so here's x, right? Here's x squared, x cubed, right? And, as you go higher and higher and higher, it gets steeper and steeper and steeper until eventually the limit function's actually this. That's the limit of that sequence of continuous functions. I could see this being relevant to your real analysis test, yes. Right? Have you guys talked about sequences of functions in there? Is this something you do? Okay. Not of functions, more of sequences, right? Yeah. Okay. But here's the example. I mean, is a sequence of each function in the sequence is continuous, and yet the limit function is not, right? This is annoying. Can we fix this? All right, and he also points out that he says he also has an example of a function which is between 0 and 1 for all x. It's monotonically decreasing as n goes to infinity, and yet the limit function is not Riemann integrable. He says he'd also like to be able to exchange the order of integration and the limit. And he says, well, it turns out that with Lebesgue integration, we can solve both this problem and the previous one. All right, so this is not actually what he's talking about. And then he brings up the issue of length of curves, and he says that the curve is rectifiable if its length L is finite. What's the length of a curve? He says, suppose we consider a continuous curve gamma in the plane given parametrically by x of t, y of t. A less than or equal to t less than or equal to b. What does it take for this continuous curve? What does it take for that to be rectifiable? He says, we define the length of gamma in the usual way as the supremum of the lengths of all polygonal lines joining successively finitely many points of gamma taken in order of increasing in t. So if this is a picture of gamma, right, the length of that, if it is rectifiable, is formed by forming, polygonal approximation of it like this, right? I mean, they could be evenly spaced or not, but they have to be, increasing values of parameters. Maybe this is, this is t equals to a, the other one's t equals to b, right? And so what's the length? Yeah, it's not the limit, it's is it the supremum or the infimum? So I believe it's the infimum of all possible polygonal approximates of the curve. If that infimum exists, it can't be, oh, yeah. So what do I want? I don't want, you're right. I see what you're saying. Supremum? Yeah. Thank you. And talk me out of it. Yeah, you're right. Otherwise, it'd just be the length of the line segment connecting the initial and final points, which would be not especially connected to the curve, right? So if this exists, right, then the curve is rectifiable. This is not going to help me get to my goal of getting further in this chapter, but I can't help it. If we think about this triangle, all right, so the curve I'm trying to describe is not pictured yet. I want the curve to be the limit, whatever that means. Maybe that doesn't make any sense. I don't know, but here it is. So of course, distance 4, distance 3, right? If I do then this, then this, then this, then this, it's still distance what? Still distance 7, right? If I do this, then this, then this, then this, then this, then this, then this, still distance 7. If I do this, then this, then this, then this, then this, then this, then this, this, then this, then this, then this, then this, then this, still distance 7. If I do this, then 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 this, and this, still distance 7. If I do, I think you see where I'm going here, right? It's very relaxing. It's not helping us cover this chapter, but it's very, very relaxing. Oops. I tried. So I want to think about the limit as the stair steps get smaller and smaller and smaller and smaller, every step, sum of the vertical and horizontal steps is 7. The Cantor set? You're right, this has something to do with the Cantor set. I don't exactly understand that connection at the moment, I'll be honest. But I think you can all agree that, it sure does look like the limit of this stair-stepping is that, up to the limits of my artistry, red line. So if the length of every one of the stair steps, right, the length of the nth stair step is 7 for all n, right? And yet the limit as n goes to infinity, right, of the length of Sn, it wouldn't seem to be equal to the length of the limit as n goes to infinity of Sn. Of course, the question is, what do I mean by that limit? This much is true. You can definitely get arbitrarily close to the hypotenuse by taking the stair steps far enough out, right? So that the distance, if you take you can make the distance between the stair step path and the, you can make the maximum distance between the stair step path and the hypotenuse as small as you like. So it seems intuitively reasonable to claim that this is the hypotenuse, right? And the length of the hypotenuse is what? It's 5, right? And yet, at every n, this is 7. And the limit of a constant sequence is 7. This is a disturbing example, really. So why is the length of the limiting path not equal to the length of the approximating path? Is it an approximating path? Does it fit this? Are we putting the points on the stair step on the hypotenuse? Some of them, right? And infinitely many of them, in fact. But that doesn't cut it, does it? Because the points which are off the hypotenuse, right, are creating this mess. The formula for arc length doesn't apply to this because the the bottom line is I'm not approximating the curve with what we say we're supposed to, which is a polygonal, this is not what's happening. We're not really rectifying the hypotenuse. We're doing something else that seems to be getting close to it, but it's actually a lie. I don't know. There's various ways of understanding why this is wrong. That's my current way. But Therefore what?
Infinity is impossible.
Oh, I didn't say infinity is impossible. I just said that care must be exercised when we're exchanging limiting processes. And calculating the length of a curve is implicitly a sort of limiting process because it's taking a supremum over a whole set of things. Right? So anyway, then he says, okay, so differentiation and integration are inverse processes, right? So whatever new notion we have of integration to possibly fix some of these problems. I don't think I've made the problems clear on the board today. I'm sorry about that. You know, we do want integration and differentiation to be inverse process. And he says, so to put matter clearly, the fundamental issue here that must be understood in order to try to raise all the questions, which I have only partially raised, is basically in 2 dimensions the problem of assigning to each subset E of R2 its 2-dimensional measure, M2E, which is essentially its area, extending the standard notion defined for elementary sets. And he said, let us instead state more precisely the analogous problem in 1 dimension. So what would a 1-dimensional measure M1 equal to M? He says, well, we're looking for a non-negative function M defined on subsets E of R that we allow to be extended values. We want, and so he starts listing the properties he wants for this measure, all right? So what should a measure, let's see here. I don't think I've really motivated this worth anything, but that's, my apologies for that. Let me, you write down the properties he wants for the measure. All right. So he says he wants measure M to assign, you know, something in 0 to infinity. Infinity is included. The measure could be infinity for each subset of R. All right. So here's some things it should behave as the following. So like the measure of E should be equal to B minus A when we let the subset just be the closed interval from B to A. So like one thing it should, so the measure is going to generalize the notion of length, right? So like what's the length of a closed interval? It's just the difference of the endpoints. That's one thing we want. Another thing we want is that if E is a countable union n equals 1 to infinity of En, then the measure of E should be the sum n equals 1 to infinity of the measures of En. Yeah. 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 I just did it. Although I don't see that notion. I don't see that notation in here either. Fair enough. So, well, there's more to this here. E1, E2, disjoint. All right. If they're disjoint, then the length of a disjoint collection is the sum of the lengths of the disjoint sets. All right. And I mean, of course, he says, you know, special case of this would be if E was equal to E1 union E2 with those at disjoint, right? Then the measure of E would be the measure of E1 plus the measure of E2. But then he points out, but that's not going to be enough for the games we're trying to play here, because we're really interested in studying how sequences what happens with sequences and sets of, a collection of subsets. We want to see what happens with the measure of like a collection of subsets. So it's not enough to just know what happens for like a finite set of them. I need to know what happens for like a countable collection of them. Right? So like what I just wrote down isn't going to be enough. But there's another thing that we should expect, which is that the measure can't really tell where it is. So if I take the measure of, something like A plus H, comma, B plus H, it should be equal to the measure of AB, Or if you like, we could write it this way. The measure of H plus E should be equal to the measure of E. If you define adding to a set as just adding H to every element of the set. This is the so-called translation invariance of the measure. These are properties that we want for this concept of measure. All right. And I've stated it just for R, for the sake of being comfortable. But actually what we're going to develop here is at least I'm trying to discuss what we want instead for not just R, but RD. Right? And so this is what we need to build a intelligent theory of integration for functions over RD. So D plays the role N usually does in my talking, but I'll try to stick with D since he uses D in this book, okay? And then he gives a wonderful, he says the basic result of the theory is the existence and uniqueness of such a measure, which is called the Lesbegue measure, when one limits oneself to a class of reasonable sets, the quote-unquote measurable sets, all right? This class of sets is closed under countable unions, intersections, and complements. It includes closed sets and also open sets, and so forth. So that's where we're going. We want to describe the Lesbegue measure, which we're going to see satisfies these. And as he says, open sets are Lesbegue measurable, closed sets are Lesbegue measurable, and also countable unions and countable intersections of Lesbegue sets are also measurable. So right there, right off the bat, before I say anything else, you can already see that this is not quite the same as topology. Right? Because topology at its start says things like, you can take arbitrary unions, but only finite intersections. This concept of measurable sets is a little bit different. It only allows for countable unions, but you also get countable intersections of, you get countable on both ends, both unions and intersections. All right. Also, a disclaimer I should make. The next chapter, he about the next 5 pages or so, he describes open and closed, limit point, and so forth and so on. We've done all of these things before. I'm going to skip past that. In short, his notion of open and closed is the Euclidean notion, the metric notion. All right. So when he talks about an open set, he's not allowing the possibility of it being open in like the sense of the discrete topology. I'm pretty sure there are things he says in here which would be wrong if you take a more general topological viewpoint. So we should always understand things he's saying going forward in this book as being said in the context of the standard topology of RD. All right? So that's just a cautionary statement. Let's get to it. So what he does in the next chapter, which is on quote-unquote measure theory, is he proceeds to describe what's called the exterior measure. So the exterior measure, which I'll try to be brief on. I'm going to state what it says, but so first of all, some of these things we just need. Rectangle. What's a rectangle? There you go. That's a rectangle. Right? What's a cube? So all the, that would be a cube. What's the volume of a rectangle? So yeah, he denotes this like this. And you say the product of the lengths of the sides here, that would be B1 minus A1, B2 minus A2, BD minus AD, right? That's the volume of a rectangle. What about a cube? I guess he uses Q for cube, which I guess makes sense. So he says for Q, with B minus A equals to L, notice that the volume of Q is equal to L to the D. All right, nothing especially exciting here, but all right. A union of rectangles is said to be almost disjoint. What's that mean? Almost disjoint. Almost disjoint, if what? If the interiors, right, of the rectangles are disjoint. What's the interior of the rectangle? Right, so to get the interior of R would be the product I equals 1 to D of A sub I, comma B sub I. I'm tired of writing the other. There you go. Although I guess people usually don't use that pi. They usually use this here for Cartesian product. Anyway, yeah, that's the open lemma. I'll do it over here. Lemma 1.1 says that if a rectangle is the almost disjoint union of finitely many other rectangles, then the volume is what? Right, yeah, it's just a sum, k equals 1 to n of the volume of each of the subrectangles. And he actually has a proof of this. Like, okay, well, great, good. But that seems eminently reasonable to me. Lemma 1.2, if R1, R2, Rn, big N, are rectangles, then, well, and, grief, and if I can just, and R is a subset of the union K equals 1 to N. Now we're dropping the disjoint interior condition. What does this give us? What's that? Right, less than or equal to the sum K equals 1 to N of the length of R. I mean the volume of RK. Just to give you a stupid picture of lemma 1.2, I can't help myself. So if this is R1, and this is R2, and this is R3, and this is R4, right? And R is a subset of those. Its rectangle is a subset of those. That means it looks something like, I don't know, could be this, right? That could be R. Then the volume of that has to be less than or equal to the sum of the volumes. It's pretty neat that if they have disjoint interiors, then it has to exactly match it like that, right? If R is formed by the union. So, lemma 1.2. All right. That brings us to theorem 1.3. I probably didn't really need to write those things down, right? You guys would have understood those. But I think it's best if I do write things down. So theorem 1.3 says every open subset O of R can be written uniquely as a countable union of disjoint open intervals. All right. Great. He says, what does that tell us about the measure of an open set if this theorem is true? Well, I'm sorry, I'm getting ahead of myself. We haven't defined measure yet. Yeah. Okay, so that's just a theorem. Theorem 1.4. We have that every open subset of d-dimensional, drd, d greater than or equal to 1, can be written as a countable union of almost disjoint closed cubes. I tell you, when I read this, it bothered me. Like, you mean to tell me you can form an open set from closed sets? Countable union of almost disjoint closed. I mean, how does, right? But he describes in gory detail here how to do it. In terms of taking a lattice and selecting, sectors inside or outside your closed, in your open set, and successively, including or excluding closed cubes until you get closer and closer and closer to the open set. I mean, he really does it in gory detail here. It's not wrong. He says, there was a follow-up to Theorem 1.3, which was that it would be natural to assign the measure of O. Well, what would define the measure of such an open subset? He actually says that. I'm trying to stick with his discussion here. So we have defined the measure, the exterior measure, right? Quote unquote exterior measure. Have we defined the exterior measure? We've not yet. I'm sorry. I have spent many hours reading this book, and I have forgotten where I am in the book as it relates to the conversation I'm currently having with you. My apologies. But he eventually defines this m sub star thing, all right, which he'll call the exterior measure. And when he does that, it's going to, reproduce this among other things. The length of an interval being. All right, I'm going to go on. So, I'll read this paragraph. He says, once again, if the open set is the union, j equals 1 to infinity, of rectangles where they're almost disjoint, then it's reasonable to assign to that open set the measure, what would if these closed cubes were like Cj, right? Or, oh no. Sam has a it's not enough for Sam not to show up for this class. Now he's doing this to me. He will rue the day. Let's see here. I will find a way. I will get back. I will have my vengeance in time. Okay. So what I was trying to say is, it would make sense to say that the measure of this open set would just be the sum, j equals 1 to infinity, of the measure of whatever your closed cubes were, right? So I would just you could think about defining the measure of the cubes to be whatever their side length was to the d power. That would be the length of the jth one. And we don't have any expectation that this has to be finite. All right. You could have a open set which goes on, and then it would have infinite measure, and that would be okay. That's one thing that could happen here. All right. He says, the trouble though is, okay, so great. You could maybe he thinks, okay, in principle you could assign the measure using this countable union of almost disjoint closed cubes, right? And his construction of the disjoint closed cubes is, you could imagine doing it a little bit differently. And so then the question is, if you found a different selection, it's not hard to look at like an open set and think about writing it as the union of a different set of disjoint closed cubes, right? Or disjoint open. So then the question is, why would the measure be independent of your, finding the cubes inside the thing? How would you know that a different selection of cubes building that open set would give you a different measure, right? That's one problem that's sort of in our way here, in this way of thinking. And then he comes to he says we come to an important example in R. So, well, anyway, it says the general theory developed in the next section actually yields a notion of volume that's consistent with the decompositions of open sets of the previous two theorems and applies to all dimensions. Before we come to that, though, we have to discuss an important example in R, and you'll be happy about this. So we are now to the Cantor set. So what is the Cantor set? Well, we'll start with C0. C0 is 0 to 1. C1 is 0 to 1/3 unioned with 2/3 to 1. C2 is 0 to 1/9 unioned with 2/9 to 1/3, right? Unioned with 2/3 to 7/9, unioned with 8/9 to 1. So what can we say about, I mean, what's the relation of these? You could continue in this fashion. Deleting the middle third. Of each disjoint closed subinterval. Of CK, right? I mean, you can see that C0 is the universe in which we're playing, right? And you can see that that contains C1, right? And that C1 contains C2, right? And C3 is a subset of C2, right? Although I haven't written down C3. And so the Cantor set is equal to the intersection n equals 1 to infinity of C sub n so constructed. Now, if you're not paying close attention, you might be tempted to think that that's just the empty set. I mean, like, but you keep deleting stuff, so how is there anything in there, right? Why is that? Why is it wrong? Can you tell me a point that's in the Cantor set? Give me some examples of points in the Cantor set. Let's call this thing C. 0 is in the Cantor set, right? What else? 1. Anything else? What's that? 1/3. 2/3, right? Right. Any number between 0 and 1 which appears as the endpoint of some subinterval in one of the nestings forming the Cantor set is in the Cantor set. So if it ever appears, if you actually write it out like this, and it's a number that appears in there, then it's in the Cantor set. So once you start seeing that, you start realizing, oh, there's a lot of things in this set, right? It's hard to describe them in our usual kind of, oh, here's a formula for it sort of way, but, you know, it is a non-trivial set. All right? And what else does he have to tell us about it? He said, despite its simple construction, the Cantor set enjoys many interesting topological and analytical properties. For instance, it's closed, it's bounded, and hence it's compact. All right? He says it's totally disconnected. Totally disconnected. Given any 2 points, x and y, there exists some point between them which is not in the set. This is what he means by totally disconnected. You give me 2x and y in the Cantor set, there is some z between x and y which is not in the Cantor set. So it's completely disconnected. And he says it's perfect. Now perfect is a new term. Perfect means no isolated points. All right, that's. So he says we turn our attention to the question of determining the size of the Cantor set. Right? He says in terms of cardinality, it's rather large. It's not even countable. Whoa, that's surprising to me. I would have thought that it's countable. It's not a countable set. This is not a countable set. What? Really? It's an exercise, huh? He says, however, from the point of view of length, the size of C is small. He says the Cantor set has length 0. And here's how he says, here's how we should see that from the following intuitive argument. He says it's covered by sets CK whose length go to 0. So CK is a union of, let's say, IK, 2 to the k of these. Of length what? One over. Yeah, 3 to the minus k, right? So that makes the total length, the measure, if you will, of CK. Not that we've defined it yet, right? But at the moment, we're just thinking measure is length, all right? And so the measure of CK would be 2 over 3 to the k, because we've got 2 to the k disjoint things, each of length 1 over 3 to the k. So if you add those disjoint things up, and we should have that the length of a countable union of disjoint things is the sum of the lengths, right? That would give us that the length of the kth Cantor nesting is 2 over 3 to the k, but the Cantor set is the limit as k goes to infinity of this. What's the length of C then? It's the length of 2 over 3 as k goes to infinity, which is just 0. So this set should have measure 0, as it's known. Its length is 0. All right. Finally, now we get to the exterior measure. M star E. E is any subset of RD. The exterior measure is the infimum of the sum j equals 1 to infinity of Qj. This is for any E which is a subset of RD. This is the definition of the so-called, oh man, I think I killed my computer. Did I ever give you guys the?
You opened it, but you didn't give us the number.
Son of a gun. Six, 4, 4, 5. I've done this so many different days in here, because what we're talking about is so infinitely more interesting than this. Although I'm kind of pleased with myself for not doing it until Jonathan left. In fact. We'll teach him. We're going to teach him. Ha-ha!
Why do I have to do this?
It's just fun. It's for your learning. Just double? Should we stop it? That was my computer dying. I was at 6% battery. All right, guys. This infimum is taken, he says, over all countable coverings of E, all countable coverings E by closed cubes. The exterior measure is always non-negative, but it could be infinite. So in general, we have that 0 is less than or equal to m star E is less than or equal to infinity. All right. He says it's important to notice that we can't just use finite sums in the definition. All right. That this is the quantity that would be obtained if one considered only coverings of E by finite unions cubes is in general larger than m star E. But you could replace the cubes with rectangles or balls. All right. Okay. Let me see if I can picture what's going on here. Why is this called the exterior measure? So if E was this, right, then the cubes we're talking about, they might look like, I mean, here's an example. I guess they don't have to be the same size, do they? But they should be cubes, which in my case would be squares. Oh, they don't need to be disjoint either? Yeah. I suppose the, well, anyway. But it's the infimum. But obviously, you'd like to take them disjoint if you want to actually find the inf, right? If you want to make that as small as possible, then certainly overlapping your cubes is not a good move. It's definitely going to make it bigger than it would otherwise be, right? So it's called exterior, though, see, because the covering of the cubes, it goes a little bit possibly past the edge, right? Past the edge of the E we're covering, exterior measure. And, great, so example 1. Example 1, he points out that the exterior measure of a point is 0. Example 2, he calculates the exterior measure of a cube is equal to the, well, it's in our notation, it's the volume of the cube. Example 3, he points out that if Q is an open cube, this is a closed cube. Let me just say Q sub, if we take the interior of the cube, guess what? It's still the same exterior measure. The point that a point having measure 0, he says, is clear once we observe that a point is a cube with 0 volume. Did you guys get that? What is the point is letting Q equal to P1, P1, P2, P2, PD, PD. That's the cube. Why is it a cube? Because the length of every side is 0. What is this